properties of LTI systems in terms of its impulse response h of n. Okay, so how to interpret, for example, causality is that you recall that for a causal system, the output of such a system depends only on the present and the past values of the input to the system. This implies that the system cannot anticipate the future. Now, what does this implies? What is the implication on the impulse response of the system? So if you recall, we have already represented the output of such an LTI system in terms of convolution sum. Okay. Now, you see, for a system to be causal, y of n must not depend on xk for k greater than n. What does this mean is that to compute the output y of n, that is the present output at time index n, you cannot invoke the future samples of k. Okay, so system should not be able to anticipate the future, right? So for k greater than n means that to compute the present input, present output n, you are invoking the future. If the requirement to compute the output such that if k is greater than n, then you need the future samples of the input. Okay, which is not possible. So that means this summation has to be limited to, you have to limit the upper limit. Okay, so xk can't go beyond n. Okay, you can't have infinite. So you see k is varying from minus infinity to plus infinity. You have to limit this. So from it should be from minus infinity to n. Okay, and then h of n minus k. So you have to you have to modify the limits if the system is, of course, both linear, time invariant, and causal. So this is LTIC. So there's another. So there are three properties associated with the same system. So one is linearity, then you have time invariance. So this linear time invariance is where this representation comes from. So for linear time invariant system, the convolution sum holds, and if it is causal, then you have to set the limits accordingly. Okay, so you see, by using the convolution sum and integral in case of continuous time system, we can relate this property to the corresponding property of impulse response of the LTI system. So you see how we do relate this in terms of the impulse response is that for this range of k minus infinity to n, h of n minus k can't take the argument, can't take the negative argument, which means if k, you see, if k is bounded by n, okay, k cannot be greater than n, then this should imply that that n minus k is always greater than 0, right? Is always greater than 0. What does this implies? Well, this implies the situation over here. Okay, this implies that h of n is 0 if it takes a negative argument. Okay, because when k is going to become greater than n, then n minus k becomes negative, right? So in terms of the convolution sum, all of the coefficients of hn minus k that multiplies the value of xk for k greater than n must be 0. So this then requires that the impulse response of a causal discrete time LTI system satisfies the condition. Now intuitively, well, this convolution sum, so from convolution sum we have derived this condition on the impulse response of the system. You see, we know already what the causal system is, but what we are doing is we're trying to use the convolution sum, which represents an LTI system, to find the property, to find how the impulse response represents a causal system. Okay, how the impulse response represents or interprets a causal system. So the interpretation is that your h of n is 0 for the negative time indices. Okay, it cannot take a negative argument, right? Now intuitively what it means is that, as you know, that for such a system, delta n is applied at n equal to 0. Okay, so the system is both linear time invariant and causal. So if it is LTIC, then that delta function is applied at n equal to 0 only. So otherwise it is 0, right? Therefore this implies that your output h of n will be 0. This should be 0 for n less than 0. Well, what does this mean is that this, again, the system is not anticipating the future. It means that your output cannot come before the input is applied, right? So h of n is 0 before the input is applied. So the system is not anticipating the future, right? It doesn't know when the input is going to be applied, right? So the system is going to respond only at the instant when the input is applied, right? So the impulse response of causal LTI system must be 0 before the impulse occurs, which is consistent with the intuitive concept of causality. So since we are talking of the impulse response, we are discussing the causality in terms of the impulse response of an LTI system. That means the impulse response should be 0, okay, before it should be 0 before the unit impulse is applied, right? So it cannot anticipate when the impulse is going to apply. So uh, the general situation is like this. So for example, if the system is at rest, it is initially at rest up to a certain time, okay? Up to a certain time it stays at rest. Then the response of the system will be 0, nothing, okay? The output will be resting conditions for it unless you apply an input or an excitation. So the system, before applying an excitation, cannot predict the output, right? It's not going to respond to that excitation, okay? So what it means is that more generally, causality for a linear system is equivalent to the condition of initial rest. So if the input to the causal system is 0 up to a certain time, then the output of the system must also be 0 up to that time. That means whatever happens after that time, after let's say n naught or t naught, if an excitation or an input is applied, the system is going to respond to that, but it's not going to respond before the input is applied. Okay, if the system responds before the input is applied, that means the system knows that input is going to be applied, so the system responds. Well, that is not possible. That is not realizable. Okay, so the system stays at rest. Okay, unless or it maintains the conditions, maintains the same output. Okay, unless the excitation is applied, so the system responds, right? So that means for the impulse response, which is applied at n equal to 0, have an output before delta n is applied. So h of n should be 0 for n less than 0. This is the condition for LTIC system. And remember that this discussion is only valid for linear time invariant system. Okay, if it is not linear, well then, well, this is not the case. Okay, for example, now it is important to emphasize that the equivalence of the causality and the condition of initial rest applies only to linear systems. For example, you see this system y of n equal to 2xn plus 3 is not linear. Why it's not linear? Because if I make this input go to 0, okay, well, the output is not 0, right? I mean, it does not satisfy, first of all, homogeneity. Okay, if you scale the input, the output is not scaled by the same scalar. If you apply superposition, you can see the system is non-linear, right? It doesn't obey superposition, it neither obeys homogeneity. System is not linear. Now, however, it is causal. Why it is causal? Because to compute the output, system doesn't require any future value of the input, right? So it is indeed causal, but it is non-linear. So let's see what happens for the what is the interpretation in terms of the impulse response. So if it is causal, then in fact it is also memoryless, okay, because you don't need any other value of the input apart from the present input sample. So on the other hand, if x of n is 0, well, y of n is not 0, right? Y of n is 3. So it does not satisfies the condition of initial rest. It's not an initial rest. So this condition of initial rest is only applicable to linear systems. It does not apply to non-linear systems. Okay, it doesn't apply to non-linear systems. So again, for a linear time invariant system, from the convolution sum, you can derive that h of n should be 0 for n less than 0. Okay, because you have to modify these summation limits, and analytically you can see that h is not going to take any negative arguments. Okay, if k is greater than n, then that means you are talking of negative arguments in h. That is not possible. Okay, that means h of n is 0 for n less than 0. All right. Okay. Now, for a causal discrete time LTI system, the condition on the impulse response implies that the convolution sum representation becomes, okay, so we have already seen that, we have already modified the limit. So well, you see, it doesn't mean that h of n is 0 for n greater than 0 as well. It's not that what it implies. Okay, h of n could be anything after n equal to 0. Okay, so this is basically non-zero for n greater than equal to 0, right? So after 0, once the excitation is given, then the output could either be, it could be a finite number of samples for a certain time, or it could be for this discrete time system, or it could be infinite number of samples. H of n could be u of n, for example, so a unit step function or a ramp function, right? So it can go on for forever, but it cannot have an output before the input is applied, that is at n equal to 0, right? Okay, so you have to modify this for this. This represents linear time. Now this represents linear time invariant and causal system, right? There are basically three characterizations, three qualifications associated with the system, that is linearity, time invariance, and causality. Now, an alternate equivalent form of the convolution sum becomes, well, this comes from, if you compare these two convolution sums, you'll see that it's using the property of commutativity. Okay, the convolution sum is commutative, so it doesn't matter what is convolved with whom in what order. Well, this is also, well, that basically over here you are shifting and flipping your input sequence. Over here the impulse sequence was flipped. So over here, X acts as an impulse response and H represents an input. So you see, this doesn't matter. Okay, I mean, this is right. The output could be X convolution with H, or at the same time this could be H convolved with X. It's all the same. Okay, unless as long as the system is LTI, the convolution is commutative. Okay, we have already talked about this. Now, if you have to write this, if you have to flip the input sequence, well then h of k, it can't take negative arguments. So then you have to modify the limits accordingly. If you're using the commutative version of the counterpart of this convolution sum, then k has to start with 0 and goes to infinity. Okay, you notice that this modification of the limits of the summation is important for causal systems in terms of how the impulse response is written. For example, over here, this is Hn minus k. So therefore, k has to be less than n. K has to be less than n for the system to stay causal. Over here, k has to vary from 0. K can vary from 0 to infinity. So k stays positive, right? So h of n or k stays positive. So the interpretation is in terms of the impulse response, that h of n is 0 for n less than 0, right? So this is the condition. So you have to modify the limits if you're dealing with the causal LTI system. Now similarly, if you have this continuous time LTI system that is causal for ht equal to 0 for t less than 0, right? What does this mean? I mean, this has a very similar interpretation as we have talked of in the discrete time domain. You cannot have a response before the impulse is applied, right? So ht should be 0 for t less than 0. And in the case of convolution integral, well, that is given by, so either you can have both the integrations are the same. Either you can flip or time shift the input, or you can do that with the impulse response. Both convolution integrals will give you the same output because of commutative property, right? But now you consider this convolution integral, the first one, and you see that t should be, well, tau. It should be tau. Tau should be less than t, so that your argument of h of t stays positive. Therefore, the upper limit of the integration has to be limited to t, from minus infinity to t. You see, from minus infinity to t, h of t minus tau is going to take positive argument. Similarly, if you look at this integral, then this is quite straightforward, that tau should be between 0 to infinity. It can't be negative, so as long as the system is causal and linear time invariant. So this is again continuous time, linear time invariant, and causal system, LTIC system. So as an example, suppose the impulse response of the system consists of two samples, delta n minus 1. You can see that h of n over here is 0 for n less than 0. So this implies causality. Okay, so for n less than 0, this implies causality. This is a causal discrete time system. Causal discrete time system. Similarly, over here, unless your t naught is not negative, it's greater than 0. That means you're shifting the system by t naught. You're shifting the input. Sorry, that you're shifting the input. The system is simply delaying the input by t naught, and if t naught is greater than 0, then that implies causality, right? So it's a causal continuous time system. Okay, so even over here, this implies that h of t is 0 for t less than 0, right? For t less than 0. So both of the systems are causal in discrete time and continuous time systems, right? Unless so over here, if t naught is less than 0, then the system becomes uh, non-causal. So finally, causality of an LTI system is equivalent to its impulse response being causal signal. So over here you see ht is a causal signal, right? If this was delta t plus 1 or delta t plus 2, well, that's non-causal because t naught becomes negative, right? So over here as well, if this is delta n plus 1, then it becomes non-causal. Okay, so both of these, you get, if you view this impulse response in terms of a signal, impulse response is a signal, right? It's a signal, it's an output of the system in response to the unit impulse, right? So if your impulse response is causal, the system is causal, right? So if you have a causal output in response to the unit impulse, the system is causal, right? Now, let's talk of the stability criterion for LTI system. So what does stability implies in terms of the impulse response for an LTI system? So now a system, if you recall, we talked of it's stable if every bounded input produces a bounded output. So that means if the bounded input leads to a bounded output, this is a BIBO stability criterion. So if the input is bounded and the output is bounded, well, that implies stability. Okay, that implies stability. Now, what does this implies, or what implication does it has on the LTI system? We have to consider the convolution sum again. Okay, so in order to determine the conditions under which the LTI system is stable, so let's consider an input x of n that is bounded in magnitude. You see, boundedness has nothing to do with the length of the sequence. The length could be infinite. Okay, it could be u of n. Now u of n is a bounded sequence because the maximum amplitude the signal can take is 1, right? So if the input has a maximum amplitude that is bounded, that is finite, we say that this input is bounded. Okay, so over here you see the magnitude or the amplitude of the signal is bounded by a certain bound. For all discrete time indices, the input is bounded. Now what happens if this input is applied to an input of an LTI system? Now a system is stable if every bounded input produces a bounded output. That's the BIBO stability criterion. So to check that, in order to determine the conditions under which the LTI systems are stable, let's consider the input that is bounded magnitude applied to an LTI system. This is convolution sum. So we have to see if the output is bounded. Okay, so let's take the magnitude of both left and right hand side of the equations. And you see, since the magnitude of the sum of a set of number is no larger than the sum of the magnitude of the numbers. Well, what does it mean is that if I put a right hand side which is equal to, instead of taking the summation or taking the magnitude of the entire summation, the right hand, it is still less than the right hand side if you take the magnitude in, of the sequences wise. Okay, the impulse sequence and the input sequence. It means that some of the samples, they might be negative, right? I mean, since we are multiplying the samples of xn minus k over here multiplied by hk, some of the samples might be negative. Therefore, they can reduce they might reduce the convolution sum. The convolution sum could be smaller if some of these samples are negative. But if you put this condition over here, then none of the samples of impulse response and the input are negative. All the samples are positive. So adding all the quantities, if they are positive, then the right hand side should be greater than the left hand side, right? So this is what it means over here. The magnitude of the sum of the set of number is no larger than the sum of the magnitude of the number. The magnitude is a positive quantity, right? So these are the magnitudes. So these are all positive quantities. So y of n is still less than this. Now, you see x, if now if we allow x of n to be bounded, and if we allow that xn to reach to its uppermost bound, if all the samples are bounded by, let's say, capital B, so all the samples are allowed to reach the finite amplitude, that is B, which is a finite sample, which is less than infinity, of course, it's a bounded input, then we can write this as, it is still less than equal to, we can take B outside of the summation, and we can write this as summation over K, okay, which is from minus infinity to plus infinity, and all we are left with in the summation is the absolute sum of h of k. Okay. Now, if the absolute sum of h of k is finite, okay, now if this quantity is finite, it's less than infinity, then that implies that y of n is bounded for all n. Y of n is bounded for all n. You see, we have proved this in a forward direction. It could be proved in the reverse direction as well. So this will be a necessary and a sufficient proof that for a system, for an LTI system to be stable, for a discrete time LTI system to be stable, its impulse response should be absolutely summable. This quantity over here should be absolutely summable, or this quantity should be a finite quantity, because a finite quantity multiplied by another finite number b should be a finite number, right? It should be less than infinity. So an important criterion is that the impulse response should be absolutely summable. Okay, so this is done over here as well. Now you see the magnitude of xn minus k. If this is bounded by b for all values of k and n, the convolution sum becomes, for bounded input for all n, if this is still less than, if you're letting all the samples of the input reaching the bound b, then that would ensure that the output is bounded if this sum is finite, for all n, right? So from the above equation, we conclude that if the impulse response is absolutely summable, that is, if h of k is less than infinity, then the system is stable. Okay, so y of n is bounded in magnitude, hence the system is stable. Therefore, the absolute summability of the impulse response is sufficient condition to guarantee the stability of discrete time LTI system. Now, in continuous time, we obtain an analogous characterization. The analogy of stability in continuous system is very similar. It will be an absolute integrability of the impulse response. Okay, so for stability, the impulse response of an LTI system, specifically if again xt is bounded for all t, for all times, the analogy with the discrete time system, it follows that if for a bounded output, if you take the, for an LTI system, since the convolution is representing the convolution integral is representing an linear time invariant continuous time system, you take the bounds of both sides, and then this should be less than or equal to, again, these are the magnitude or the positive quantities. Okay, so the left hand side is still less than the right hand side, and if you allow all the amplitude or xt to reach the uppermost bound b, which is a finite quantity, over here you can take b out of the integration, so you're left with the absolute integrability of the impulse response. Then that means this absolute integrability should be finite. That implies that the impulse response should be absolutely integrable, right? So for all time t, yt is bounded. Okay. Therefore, the system is stable if the impulse response is absolutely integrable. This is for continuous time system, and for discrete time system, the impulse response should be absolutely summable. Okay. So these are the two. These again, this is not the two. It's the same condition that should hold for the LTS system in order for it to be qualified as a stable system, right? So you see that we are trying to characterize the system, and we are trying to qualify the LTI systems in terms of their impulse responses for causality, for stability, for invertibility, and if the system comes with a memory or not memory requirements. So you see, for an LTI system, the impulse response happens to be its signature, right? So impulse response is important that it completely describes the behavior of an LTS system, right? So all this discussion is valid for LTS system. Okay, we are not talking of nonlinear, we're not talking of time varying systems. Okay, Now this is an example 2.13 from the course text. So what it says is consider a system that is pure time shift in either continuous time or discrete time. Then in discrete time, your impulse response should be absolutely summable. So if the system impulse response, or if the system is shifting your inputs, delaying the input, and n naught is a positive quantity over here for it to be causal as well. Uh, then well, then the sum is 1 because this is a unit sample sequence. So you see the h of n is absolutely summable. That implies stability. While in continuous time domain, if again the system is delaying your input, okay, it's tau minus t. Well, you remember that integration of delta t dt from minus infinity to plus infinity in terms of weight, this is equal to 1. So we conclude that both of these systems are stable, which are just delaying the input. This should not be surprising. This should not be surprising. Intuitively, you see if the signal is bounded in magnitude, well, so is any time shifted version of that signal. You see if the signal is bounded. I mean, if there is an uppermost bound in the signal, it's like this. Okay, so if there is an uppermost bound like this for xt, so if you shift this, okay, if you're going to just shift this to some other call this d naught, okay, so the bound stays there, the amplitude is still there. Okay, so this shift, let's call this shift as t naught. Okay, you're just shifting the signal by a certain amount of a finite interval, by a certain finite interval. Then that means the magnitudes or the amplitudes are still there, are intact. Okay, it just shifts in time, but the bound is there. Okay, so the system intuitively is also stable. I mean, the system is just delaying the input. Okay, so if the input is bounded, the output has to be bounded. It's a stable system. Again, it follows that a bounded input leads to a bounded output if the system just delays an input by a certain number of samples or by some shift in time, right? So both in discrete time and continuous time, a system which shifts an input is BIPO, stable. So now let's consider another example. Let's consider an accumulator. Okay, we have talked about this in the last video. If you just have a look at example 2.12 over there, 2.13, 2.12 was discussed in the last video. So, so we consider this accumulator. This was an unstable system. So if you apply a constant input to an accumulator, the output grows without bound. To see this, you see system is unstable. That can also be seen from the fact that the impulse response is UFN. Now UFN is not absolutely summable. Okay, you recall the if the for example an accumulator, if I write the accumulator as x n minus k, well, just to recall how an accumulator is, there are many alternate representations for such system. One of the representation in terms of summation can be written as the summation is again over k. Okay, so k can vary from 0 to infinity, right? 0 to infinity. That means it is summing up all the samples. So you have this starting with x of n, this will be plus x of n minus 1 plus x of n minus 2. Okay, so dot dot dot, this goes all the way to x of minus infinity. So basically it's summing all the samples of x of n, right? So how do you compute its impulse response? Well, it's easy to see. Impulse response is simply you just replace x by delta. The input of the system becomes the delta function. So delta n minus k, and if you vary k from 0 to infinity, and that becomes the definition of the unit step function. Okay, u of n can be expressed as such. U of n can be decomposed into shifted pulses, infinite number of such shifted pulses that are going to start at k equal to 0 and they're going to up to infinity. Okay, so you have delta n minus 1, delta n minus 2, and this goes to infinity. So this is u of n, right? So now, if this is the system stable in terms of impulse response? Well, you see, y of n is g of n. Okay, this should be basic. This should be h of n. This should be h of n. Impulse response. Is it summable? Is it summable? Okay, it starts with n equal to 0 to infinity. It's not summable, right? I mean, if you take the absolute sum of the impulse response, it's not summable. It goes to infinite. U of n is although it is a bounded input, U of n is a bounded input, but the output is not bounded. Okay, it grows because even if intuitively, if you are looking at the this summation, you are summing an infinite number of samples. So the summation grows without bounds. So the bounded input is not leading towards the bounded output. The accumulator is an unstable system. Similarly, consider integrator, the continuous time counterpart of an accumulator. This can be expressed as yt over here, yt as minus infinity to t. Okay, and you see the reason for this is well, y of t, since your h of t is again u of t. Okay, so you can write this as x tau, and I'm going to write this as u t minus tau. Now this is my impulse response, which is delayed and shifted in time, d tau. Tau is the integration variable, and tau has to vary from minus infinity to t. Why? Because in this range, u of t is non-zero. Okay, it's one, so it's one. So we are not writing this over here. So you just reduce your integration to this expression, right? So this is an unstable system for precisely the same reason as given for the accumulator. It means a constant input gives rise to an output that grows without bound. The impulse response for an integrator can be formed by letting xt as delta t, in which case, so if you let delta t over here, well, you can see that this becomes ut, and ut is not absolutely integrable. Okay, so ut in this range from 0 to infinity, this is 0. Lower limit becomes 0, in which case this is 1. This is equal to infinity. That means h of t is not absolutely integrable, therefore the system is unstable. So accumulator system is an unstable system, whether it's a continuous time or a discrete time system, because its impulse response is u of t. It's not either summable or integrable, but if a system is delaying a bounded input, then it is stable because the output is still being bounded by the same bound of the input, right? Okay, so the last thing, let's talk quickly about the Unistep response as well of an LTI system. Well, why Unistep response is important? You see, up until now, the reason is that up until now, we have seen the representation of an LTI system in terms of its unit impulse response that allows us to obtain very specific characterization of the system properties. Specifically, since h of n or ht completely determines the behavior of LTI system, we have been able to relate the system properties such as stability and causality to the properties of impulse response. So for example, if h of n is 0, for n less than 0 implies causality. Okay, similarly, if h of n is absolutely integrable, if it is absolutely summable, that implies stability. So all the characterizations are in terms of the impulse response. There's another signal that is often used to quite often used in describing the behavior of an LTI system. That is the unit step response denoted by S of n or St, which corresponds to an output when x of n is u of n or xt is ut. So if the input is a unit step function, the output is denoted by s of n. So we'll find it useful on the occasion to refer to the step response. So s of n is the step response, or st is the step response, and therefore it is worthwhile relating to the impulse response. So how do we relate s of n to u of n? Well, if we can relate s of n to u of n, if there's a relationship, there's a simple relationship to that, that means s of n can also be used to characterize or qualify the system for causality and stability, for memory or memoryless or invertibility, right? So let's see. So from the convolution sum representation, the step response of a LTI system is the convolution of the unit step with impulse response. So by definition, the impulse response is the step response of the system is the response to the unit step function. So unit step function convolved with h of n, given the system is LTI, will give you the step response. So let's see. This step response, since the input is uk, right, which is unit step function for discrete time system, can be expressed as from k equal to 0 to infinity. Either you can write it as such, or you can see if you see that the convolution is commutative. And this expression is if you start with un minus k and hk, then that means the upper limit has to be bounded by n, right? So these two expressions are very similar. These two expressions are same step responses of an LTI system to a unit step function. Okay, now unit step function can either be And the impulse response or the signal, however you treat it, because the convolution is commutative. So by commutative property of convolution, Sn is either Hn convolved, Un, or therefore you can view Sfn as viewed as a response of an input at Hfn of a discrete time LTI system with a unit step response Ufn. Basically, if you change the order, it's not important. The order is not important. What is being convolved with whom in what order is not important. Okay. So from this equation and from example 2.12, it is clear that Hfn can be recovered from Sfn using that relationship. So you see, if you can bifurcate this summation like this. So if I have this up order tail n minus 1 from k equal to minus infinity, k minus infinity, and this is h of k, then the only sample that I'm leaving behind is h of n, right? This will be h of n. And what is this? What is the first summation? Well, this summation is precisely my s of n minus 1. Therefore, I can find a first order difference equation relating the step response with the impulse response. So Sn is Sn minus 1 plus Hn, or the impulse response is the first difference. So that is the step response of the system minus the immediate past step response of the system. So you have to recall what is at n minus 1, what has been accumulated up till n minus 1 discrete time instant. Okay, take the difference from the present sample, that is the impulse response. So that is the step response of a discrete time LTI system is the running sum of its impulse response. How it is the running sum? Just see over here. It refers to this equation. S of n is summing up all the samples of the impulse response, and conversely, the impulse response over here is the impulse response of the discrete time LTI system is the first difference of the step response. So they have a relationship. They have a one-to-one relationship with the. So if you know, for example, the step response, you can find from step response your impulse response of the system. And if you know the impulse response of the system, you can find the step response by summing all the samples of the impulse response from minus infinity to the present index n, right? So they have a one-to-one corresponding one-to-one relationship. So similarly, in continuous time, the step response of an LTI system with an impulse response ht is given by st ut convolved ht. It's also equal to the response of an integrator with an impulse response ut to the input ht. That is the unit step response of a continuous LTI system is the running integral of its impulse response. So similarly, there is a correspondence. You see, st is given in terms of the convolution integral when the input is ut. Okay, it can be flipped and time reversed to produce a convolution integral. So again, you change the limits from minus infinity to t, where ut minus tau is unity, and therefore this is simply a running integration. Okay, so it's a running integration of the impulse response from minus infinity to t. And also in terms of ht, if you take the derivative of both sides, ht is simply the derivative, the first derivative of the step response. So hence the unit impulse response is the first derivative of the unit step response. Impulse response is the first derivative of the unit step response. So there is a one-to-one, again, a relationship that exists between the step response and the impulse response in both discrete time and continuous time domains. Therefore, in both continuous time and discrete time, the unit step response can also be used to characterize an LTI system, since we can calculate the unit impulse response from it, right? That's all.